Hello everybody, and thanks for joining us in this, which is the fourth of our webinars for 2014. My name's Tom Pritchard, and as always I'm the host for today's event. I will be introducing the webinar and also rounding up at the end. So today's presentation is entitled The Advanced Modelling Features of LimitState Ring, and it will give you a flavour of some of the less widely known about but some extremely useful applications of the software. This includes, amongst other things, how to diagnose the causes of existing cracks and identify potential load paths under service loads. The total time for the webinar is about 1 hour, and this includes 5 to 10 minutes at the end for any questions that you may have, which you can post at any time using the question functionality that's present in the webinar interface. We do try to answer as many of your questions as we can in the time available, but this isn't always possible. I do apologise if we're unable to get to yours, but if we don't, please feel free to contact us outside the webinar via info@limitstate.com, and we'll be happy to answer them for you then. So, without further delay, I'd like to introduce our speaker for today, Professor Matthew Gilbert, who is the LimitState Ring Product Manager, and I'll now pass you over to him.
Thanks very much, Tom, and thanks everybody for attending this webinar. It's the last in the 2013-14 schedule of Ring webinars. So the title is Advanced Modelling Features. I think perhaps it could have been better titled The Less Frequently Found Modelling Features of LimitState Ring, features that many people are perhaps not aware are present in the software. Okay, so what am I going to cover? For those of you who are not familiar with the software, I'll just tell you a little bit of background. And also for those of you not familiar with LimitState, again, I'll just give you a little bit of background to who LimitState are, what we actually do. In terms of the main body of the webinar, the three advanced modelling features which I'm going to focus on are modelling local details of a bridge, a little bit about the support movement mode, which is probably the #1 feature that people are not aware of, and finally a little bit about how we can model reinforcement using the software. And I'll wrap up with some conclusions. So apologies to those of you who have been to the last couple of webinars. For the first few slides, I just want to say a few things about LimitState, the company which develops the software. Basically, it's a spin-out from the University of Sheffield, been around for getting on for 8 years now. We're commercialising academic research. We're focusing particularly on powerful software for the ultimate limit state, primarily the analysis at present, but there's plans for design software as well. The kind of secret sauce, if you like, is that we're using optimization technology to identify solutions. That's quite different from most players in the fairly crowded analysis marketplace. Pretty focused on ensuring the software is robust and well validated, and as a spin-out company we're able to fully support software and also spend time making sure it's as easy as possible to use. So just a quick sort of view of where we are in the sort of vast array of engineering analysis software tools. Really, we can categorize most tools as either being a traditional tool, in other words, an automated hand calculation tool, potentially embedded in a simple program or spreadsheet, or at the other extreme, an advanced tool which might use non-linear finite elements, discrete elements, or other advanced numerical methods. We've identified a gap which we think we can fill with what we're calling computational limit analysis tools. The main benefit of computational limit analysis is that we can have arbitrary geometries, we can identify arbitrary failure mechanisms, but we can do that pretty much instantaneously. So we have the usability associated with traditional tools, but with a good deal of the power that's associated with advanced tools. This particular example, we're talking about a geotechnical problem, so it could be slope stability, retaining wall stability, but we could be talking about slab analysis. We're planning in 2014, after some delay, releasing a slab analysis software. application, or it could be what we're focusing on today, masonry arch analysis. LimitState ring, it's been around, well, as LimitState ring since 2007, but it builds on research software which was made available in 2001 and is very widely used around the world. Clients for LimitState ring are numerous. There's a handful shown here. In terms of the benefit, one of the most obvious benefit you can see on the slide is that you can visually see the potential failure mechanism. So it's very, very clear what the potential failure mechanism is for a particular loading configuration. And in terms of the geometry of the bridge, the program doesn't care whether you're dealing with a single span bridge or a multi-span bridge. It will identify the most critical failure mechanism regardless. Our current main software tool is called LimitState Geo. It's geotechnical software. It's launched in 2008 and it's now at version 3.1. And similar to LimitState ring, it allows a very clear indication of the expected mode of response at collapse. In a sense, it extends the functionality of LimitState ring by allowing potential failure planes to form within the soil mass rather than simply at the locations of joints between masonry blocks. And again, the software is used by many major companies around the world. Okay, so moving on to masonry arch bridges, a bit of background. Many of you will be aware that these kinds of structures are very commonplace. We reckon there's about 1 million spans worldwide, many particularly in Western Europe, also many in, for example, China and the Far East, and also a sprinkling of bridges in many other parts of the world, for example, East Coast of America, Iran, Australia, and so forth. Key thing is that they're in many cases carrying traffic, whether that be highway traffic or railway traffic, and we need to check that they're still fit for purpose. So we need to assess these bridges and take remedial action on an intelligent, focused way. So just going to a little bit of a basic theory. How do arches stand? The nice bit of work done by Robert Hooke, probably close to half a millennia ago, goes something like this. As hangs a weightless chain, so but inverted, stands the masonry arch. So in other words, if you get the voussoirs that you're going to use to form your masonry arch with, you suspend them from a weightless chain or cable, you look at that profile, you invert it, and you find that you can fit that profile within the thickness of the masonry, then you've got an assurance that your arch is an appropriate shape to carry at least the self-weight of the masonry. So what we've got now is a line of thrust, a line of compression, and key observation is that there are various possible lines of thrust. We don't necessarily know which line of thrust is active at any given time. However, if we apply an external applied load and we gradually increase that external applied load, we get to a point where we can only just fit the line of thrust within the thickness of the masonry. If we apply any more load at all, then we get hinges forming and we get a collapse mechanism. So As far as we're concerned, this means that although there's some uncertainty about how a bridge is carrying service loads, we can say with a bit more certainty how the bridge is likely to collapse under the action of an overload. So just to summarize that, in service, many possible lines of thrust or equilibrium states. If, on the other hand, the supports move, then we can identify a unique line of thrust. And this corresponds to the support movement mode in limit state ring, something which we'll talk a little bit more about later in the webinar. At collapse, you have a single limiting line of thrust or equilibrium state, and we can calculate a value of applied load or multiplier on the applied load required to cause collapse. And this is sort of standard or normal mode in limit state ring. So considering the latter, how do we find the collapse load? Well, of all the permissible equilibrium states or lines of thrust fitting within the arch geometry, we can use optimization to find the one that corresponds to the maximum load factor. And that's basically what the software does. In terms of mathematical equations, what we're basically doing is we're maximizing a multiplier on the applied load subject to equilibrium and yield constraints. The nice thing about that is it boils down to a simple linear optimization problem which is very straightforward to solve. Clearly, an arch bridge isn't simply a masonry arch. There's also other elements. For example, we have soil infill. How do we model those elements in the software? Well, we actually model the anticipated effects of the backfill rather than the backfill itself. And the anticipated effects are that we get spread of the live load through the fill, and also when the arch barrel starts to sway, then we mobilize passive restraining pressures. We model those passive restraining pressures through what we refer to as backfill elements. And the backfill elements resist movement if the barrel moves into them, but they have no effect if the barrel moves away from them. And that's basically saying that we take account of passive pressures, but we choose to ignore active pressures because they're significantly smaller than passive pressures and make very little difference to the predicted load carrying capacity of the bridge. So here's an example bridge modeled in the software. So you can see we've done an analysis. We have a line of thrust or a zone of thrust representing how the bridge is carrying the load at collapse. We've also got hinges shown in red. We have backfill elements which are providing passive restraint, highlighted in blue. The other elements, the non-active ones, are shown in light colour. And this gives you a kind of a good idea of the key elements of the software in action. Okay, so that was a kind of a whirlwind tour of the software in terms of the key elements of it and how it works in principle. Now move on to the main topics that we're going to cover in this particular webinar, starting with the first of these, which is how do we model local details of a bridge. So if you haven't used the software before, or if you haven't used this particular aspect of the software, then the key thing to point out is that the property editor that appears on the right-hand side of the screen when you use the software is the gateway to modelling local features. So pretty much anything that you can do globally, you can do locally. So for example, you can apply mortar loss in a global sense, or you can apply mortar loss in a local sense. And in a local sense, you do that by selecting a contact or group of contacts where you want to apply the mortar loss, and then you enter the amount of mortar loss that's involved in that particular case. However, I'm not going to dwell on mortar loss particularly. I think I've covered that in a previous webinar. I'm going to look at slightly more involved modelling functionality, and in particular I'm going to look at how do we model partial ring separation. Now, those of you who've come across multi-ring brickwork arch bridges know that a potential problem is that you can get delamination between the adjacent rings. And some years ago I was involved in some research in this field, and part of that research involved testing very simple 3-meter span arch ribs with various different inter-ring bonding configurations. And in the picture you can see in the foreground an arch barrel or an arch rib with good bonding between rings, and you end up getting a 4-hinge failure mechanism. In the background, the second arch rib, arch 2, has deliberately debonded arch rings. We actually have just sand between the two arch rings. In the third and fourth arch, we decided to have partial bonding. In arch 3, we actually put headers between the two arch rings, and arch 4 we actually did the same thing but replicated using an external plate. So this is arch 3, which contains the headers, and you can see that we're looking at this particular bridge during the load test. So what I'll do is I'll start the software, and I'll open Bolton Arch 1 to start with. So this is the first arch rib. Actually, you can see the standard view of the software, which assumes that you have backfill. Actually, I've effectively switched off the backfill by assigning it 0 unit weight, and also there's no dispersion. So basically what we have is a model of arch 1. If I press the solve button, then instantly I will be able to get a multiplier on the applied load, which in this case corresponds actually to a failure load in kilonewtons. If you look at the output box, you can see that we've got an adequacy factor of 3.988. In other words, around 4 kilonewtons as the applied load, which is actually very close to the experimental value, which it turned out to be 4.2 kilonewtons. What I'm going to do now is I'm going to change the geometry of this bridge so that instead of modelling the arch barrel as a single ring, I'm going to model the arch barrel as 2 separate rings. So at the moment you can see that I've got 47 units in the arch barrel, which corresponds actually to the number of bricks in my arch, and I've got a ring thickness of 215. I'm going to change that to have a a ring thickness of 107.5, but I'm going to put a second ring. So instead of having one ring of 215, I'm going to have two rings of 107.5. And now you can see that we've got the two rings and we've also got an inter-ring join. If I click solve, then I have quite a different mode of response, and I have critically a significantly reduced adequacy factor. It's now 1.47, which corresponds to a failure load of 1.47 or about 1.5 kilonewtons, which corresponds to exactly what was obtained in the experimental test. Right. Now what I want to do is I want to try to go back to what we saw in the lab and actually enter these headers to see what effect it does have on the load carrying capacity of the bridge. So what I'm going to do is I'm going to use the property editor to specify those. So what I do is I choose to select the contacts between rings where we have the headers, and the count where it is 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. That's not that one, it's the next one. So for those 5 contacts, I have shown now in the property editor the various properties associated with them. And you can see that I can choose to change to permit hinges to be false, and most importantly I can change to permit sliding to be false. So now I have effectively a model which incorporates those 5 headers that you saw in the experiment. If I click solve now, I get a slightly different failure mechanism, and I get a relatively significant increase in the adequacy factor. It's now gone up from 1.47 to 3.17. And I'll just switch off the view of the thrust line and the hinges so you can see a bit more clearly what's going on. But you can see that whereas I have separation between the rings that are not effectively glued together, there's no separation at the 5 locations corresponding to my header locations. And I have significantly increased the capacity by doing so. So how does that correspond to what we saw in the tests? Well, I've got the experimental failure loads in the first column. Arch 3 and 4 were actually nominally identical, but we had some scatter in the experimental failure load. The model for those 2 arches is the same, and you can see that the predicted collapse load is actually roughly midway between the failure load for Arch 3 and Arch 4. So that's giving me confidence that the partial ring separation model is giving us a good indication of what's going on in reality. Okay, so I'm going to move on to a more practical example. This is a very short span bridge in the field. It's a culvert over a stream, and some hammer survey was carried out, which indicated that a large proportion of the span of this bridge had ring separation. but close to the springings, that wasn't present. So I'm going to show you an example of how we can model that in practice. Here's a view of where the ring separation was identified. So it's identified throughout most of the span, but there was no ring separation close to the springings. If I open up the software again, I've got this one saved. Okay, so what I'm actually doing in this case is I'm going to run the vehicle across the bridge. So when I click solve, the analysis has been carried out at a number of locations, and when the software finds the position with the lowest load factor, it will show me that, and I'll get an understanding of what the value of the adequacy factor is. And what it's telling me is actually that my adequacy factor is 0.3, which is not good. I've got actually in this case I've got a 56.4 kilonewton single wheel load on the structure, and a correspondingly low effective width. But the capacity is relatively low because of the presence of the ring separation. What I'll do is I'll just again zoom in so you can see clearly where the ring separation has been prescribed. So it's prescribed where the inter-ring joint is black, and we have effectively glued together the inter-ring joint where we have this this purple colour. And clearly I can look at various different what-if scenarios. What would be the effect of retrofitting this bridge by actually potentially stitching the rings together? I could easily model the effects of that if I wanted. Okay, so I'll move on to the next feature that I wanted to cover, which is, as I mentioned, probably the least widely known about feature of LimitState ring, perhaps because it wasn't present in the very first versions. So it's new in LimitState ring. So the so-called support movement mode is a feature which allows you to impose movements of any or all of the supports. And two key benefits. One is that it allows you to gain an understanding of how the structure is likely to be carrying working loads. Second main benefit is that you can use this mode to diagnose the likely causes of crack patterns. So just to show you how easy it is to set up a model, I'll create a new bridge. So let's suppose we've got a highway bridge. I use the defaults. Just use the defaults, but I'll make it a 2-span bridge. I've checked the box saying insert span after this. For the pier, I'll make the pier say 3 meters high. I'll click next. I'll keep span 2 the same as the previous one, and I'll just click next, accept the default values for the other geometrical parameters. Similarly for now, I'll keep all the partial factors as unity, and I'll use the default materials of masonry, backfill, and surface fill. But what I will do is I'll choose a vehicle. Various vehicles I could choose. I could choose, for example, a EU triple axle, and I could set that here. If I click finish, then basically I've got a bridge with a load, and in the normal mode, then what happens is that the load on the bridge is multiplied up until failure is identified, and then the multiplier required to cause failure is reported. So that's the adequacy factor. If I take the load completely off the bridge, then it will try and do an analysis, but it won't have much success because it's trying to multiply up this applied load until we get failure, but it can do that ad infinitum and it still won't get the point of collapse. However, what I'm actually going to do is I'm going to move into the support movement wizard, and I'm actually going to specify that, for example, we have movement of, for example, a central pier. Let's suppose a central pier has suffered some subsidence and has moved down by 10 millimeters, for example. I do that and then click solve, then you can see that I effectively can model how this bridge is likely to respond under the action of that settlement. And it's quite common that you might find this scenario in a multi-span bridge, that the foundations under the pier are a little bit less robust, if you like, than the foundations underpinning the abutments. So supposing this situation was present in practice, what I might be interested in now is how the influence of the applied load affects how the bridge is carrying the load. In other words, how this vehicle affects the load paths. So what I'm doing now is I'm gradually moving the vehicle onto the bridge. The hinge positions you can see are shown in red. But as I move the vehicle onto the bridge, you can see that the locations of those hinges changes. Now, it's important to bear in mind that the vehicle load is unfactored. So this is exactly as we specify it. So I specified a EU triple axle. So whatever those axle loads were are now being applied to the structure. And you can see that depending on where the bridge works, or where the vehicle is in relation to the bridge, I get moving hinge locations. Now, why might this be useful? Well, sometimes you can encounter a bridge which has clearly suffered some settlements, minor settlements, is carrying quite modest loading and is quite happy doing so, and has been doing so perhaps for several decades. When the loading applied to that bridge, whether it be railway or highway loading, so sometimes you find a rapid deterioration of the structure, and you can effectively simulate the likely effects of suddenly increasing loading using software. So if you see reversal of hinges, so in other words, joints likely to be opening and closing under the action of a vehicle, then it's quite likely the bridge will suffer incremental damage, and in due course will need repair or replacement. So it's an interesting way of getting a little bit more insights into how your structure is working. So that's one usage mode. So I just went straight in there and did the analysis. You might ask, how does the software actually do the sums in this case? Well, if we start with the standard mode where we're maximizing a load factor, so this equilibrium, then just highlight the changes. So actually what we're doing is instead of actually I've just made some annotations to this. I should have said should be minimize the energy or the work done at the supports. So E is the support movement energy, so minimizing the support movement energy subject to equilibrium constraints is the same, and the additional constraint, which basically equates the energy done at the supports to the specified displacements, so that's contained in this vector D support, multiplied by the unknown support reactions, F sub. So it's a very minor change to the formulation, allows us to effectively get information about how the bridge is going to behave if we have support movements. Okay, so just go back to the main. To get out of this mode. Okay. So the next example is, I think it's the first bridge I ever applied this functionality to. It's a bridge it's a railway bridge in Paris. There's an approach viaduct to a river crossing, actually crossing the River Seine. And what appears to have happened is that timber piles supporting the approach piers appear to have gone rotten, and we have evidence of quite severe settlement and corresponding cracks. And you can see actually on this next slide the river crossing, so it's a girder span, a rather large abutment at this point. That abutment isn't founded simply on timber piles. There's caissons there, so there's no chance of that moving. But the approach piers are founded on timber piles, and those appear to have moved down. And what we see, it's quite difficult to see on just a photograph from distance, but when you're there at the bridge, it's very clear. There are cracks, and the cracks are identified on the image, as you can see. And actually, what the railway authorities have done is they've actually applied I-section ring beams effectively underneath the spans as a kind of contingency arrangement prior to rectifying the problem. So what we found is that the next couple of spans appear to have moved downwards, and then beyond that, we appear to have business as usual. So what we tried to do, actually what I tried to do on site, was create albeit a relatively crude model, and this is showing two intermediate piers moving downwards, and you can see the locations of the hinges in the spans. And so the locations of the hinges in the spans are relatively similar to the locations of hinges that we see in practice. And one other thing to say is that because of the sort of pseudo-elliptical geometry, I've assumed that there will be backing elements above the piers. And the amount of backing that I've assumed, it turns out, is quite pivotal to the locations of the hinges. So I actually did another analysis, but this time with a lesser amount of backing, and you can see that we get different hinge pattern. And actually this particular hinge pattern is less similar to what we see in practice. So this is actually pointing to the fact that probably there is a good amount of backing in this bridge, and by extension we can see this settlement as a way of calibrating our model and improving our confidence in the validity of the model for this particular bridge. And in fact, you can view a bridge with settlement as an opportunity. If you've got many bridges of the same type, then actually getting a good match for the bridge that's been subject to settlement with your model means that probably your model is likely to be capable of giving better predictions for the rest of the population of bridges of that type. So you can view it as an opportunity as well as a problem. I think in the last webinar covering row and masonry arch bridges, I showed a bridge that had been subject to quite severe mining settlement. It was a 5-span bridge, and I've just got settlement analysis of this structure below. Actually, it's a little bit confusing. I think I've got a viewing the bridge from the other direction, actually below to the photograph you can see above. So, in other words, the span at the right-hand side here corresponds to the first span, and the first span has quite severe mining subsidence. And the nice thing is that you can use this support moving functionality to try to get a good idea for the likely causes of the crack patterns that you see, and that increases your understanding of the structure that you're dealing with. Okay, so moving on then to the third and final advanced feature that I wanted to cover today, modeling reinforcement. It's a new feature in version 3 of the software. Basically, we can add reinforcement elements either to the intrados or to the extrados of the barrel, and also either on the surface or at some prescribed depth, as you can see. So in terms of the mathematics, it doesn't change the calculation significantly. You simply have additional forces acting at the contact, as you can see here. So in other words, we've got a additional compressive force, CB, which acts at the location of the reinforcement here, and additional tension force, TA, which you can see acting in the tensile region. So it's a very, very small change to the analysis formulation. And here we can see some reinforcement elements. There are some assumptions, though, you've got to be aware of. So what we're assuming is that the reinforcement behaves actually in a rigid plastic manner, and it yields at the prescribed force, and it yields in a ductile manner. We're assuming effectively that there's no debonding of the reinforcement, so it simply yields. That's the failure mode. And we also assume that the overall behavior of the bridge is similar to the before reinforcement case. So we're not allowing complex, particularly brittle, punching shear type failures to occur, simply because the software is based on plastic analysis principles, and clearly such software is not appropriate for doing analysis of a brittle phenomenon. So there are some examples given with the software that show the validation of this feature. So I think I've got one here. It doesn't look much like an arch. It's actually a reinforced beam, effectively. So I'll do the analysis, and it's quite an artificial example that the blocks in this case have been made weightless. But what I can do is I can, for example, view the shear force and view the bending moment diagram, and I can look in the appendix of the manual and verify that we get the same results as you would get by hand calculation for this type of problem. What I'm going to do is just mention a slightly more relevant validation as far as Masonry arch is concerned. Some years ago, the Transport Research Laboratory in the UK tested a series of 5-metre span bridges with soil, fill material, and they tested those with and without reinforcement of various kinds. I just want to pick out 2 bridges. One is a non-reinforced bridge with a peak load of 200 kilonewtons, and the second is a bridge with embedded reinforcement. So there was we've got a slight misprint there, I should say 622 millimeters, 12 millimeters bar at 19 millimeters from the intrados, and yield strength 480, and that gives us effectively a tensile force of 149 kilonewtons at each cross section. So if I open up the unreinforced case for this bridge, so an unreinforced bridge, and I can do an analysis, and so this is a multi-ring bridge, and clearly has comparatively low carrying capacity because of the presence of the reinforcement, the presence of the ring separation. And the question is, would it be sensible to apply reinforcement to this bridge? If I look at a given contact, you can see the various properties there, and it doesn't by default give me any information about reinforcement properties, and that's really to sort of ensure that the property editor doesn't have too much clutter. If I want to perform a reinforcement analysis, then I just simply need to go to the main dialog for the bridge and simply check this box saying bridge includes reinforcement. And then when I go to the same contact, I can see I've also got information about reinforcement that I can enter. Now, I could basically select many contacts and then apply the reinforcement, but there's a nice tool that will allow me to do that quite rapidly. It's the select tool, contact select tool. I can simply select all the contacts in the first ring using that tool. I can then enter details of the amount of reinforcement force that I have. I think I've got 149.3 kilonewtons in both the compressive and tensile senses potentially, and I've got reinforcement depth. I think it was 19 millimeters. So now, if I zoom in, I can see that I have reinforcement positioned. And if I click solve, I then get a increased adequacy factor, which actually in this case corresponds to the collapse load of the bridge, of 325. And that is extremely close to the experimental value of 320. And if I want to, I can look at bending moment diagrams or shear force diagrams. You can show a line of thrust, but you get a warning saying it's much less meaningful when you have reinforcement. The line of thrust is likely to lie outside the thickness of the masonry. You can see actually that that's the case. So we've got this line of thrust actually for the bottom ring, which is lying outside the bottom ring. So generally speaking, the bending moment is likely to be a more useful measure of what's going on in a bridge with reinforcement. Okay, I think we're running a little bit short on time, so I'll move through to the wrap up. So, three things that hopefully you've picked up in this webinar are, first of all, that the software allows local details to be modelled, for example, partial ring separation. The support movement mode allows potential load paths from the working loads to be explored, and also the likely causes of existing cracks to be investigated. And final point, reinforcement can also be modelled, assuming full strength, mobilised and a ductile failure. Perhaps just say a caveat on that. Personally, I think it's often much more fruitful to look at providing, for example, a mid-surface slab in the fill material as a way of reinforcing a bridge rather than actually reinforcing the arch barrel. There is a danger that you can trigger unfavourable and potentially unexpected failure modes if you apply reinforcement, and you can fundamentally change the mode of response of the bridge. However, if you're careful, then you can use ring to certainly give you a good idea of how reinforcement might influence the results. Okay, that concludes my presentation. Any questions? Okay, I'm just looking at the question. Okay, I've got okay, I've got a number of questions. One is, how do I model mortar loss? I did mention mortar loss, but I didn't actually show how it could be modelled. I'll just create a new bridge very quickly and show how that can be done. So, supposing I had mortar loss, for example, around the right-hand support, what I can do is I can simply select the areas where the mortar loss is. So, for example, suppose there was 100 millimeters of mortar loss, then I can model that there. Now, in this particular case, this particular failure mode, it's not going to change the result at all. But if I move the load to the opposite side, then I'm going to have a clear impact of the presence of mortar loss. Okay, second one, got several bridges where the patch repairs with stronger brickwork. Can I take advantage of this? Okay, so if you've got a bridge that's 100 years old, then very often much of the masonry is original, but some parts of it is not original. So sometimes you find that perhaps you know, a good region of masonry, for example, around the springings, has been replaced. So in this case, let's keep this example. So if I click solve here, I've got this adequacy factor of 366. Let's suppose that in this region, so the other side of the bridge, I've got very strong masonry. I can take advantage of that. I can change that from 5 to 50. And when I click solve, then it makes very little difference in particular case. Had my span been longer and my masonry strength being a little bit weaker, then I might have expected a bit more impact. But the answer to the question is yes, you can model that very easily. Okay, looking at some more questions. Okay, can ring be used for design assessment purposes of reinforced concrete and mass concrete arches? Okay, I understand that a number of ring customers are using it, certainly for the assessment of lightly reinforced concrete arch bridges. We don't, as an organisation, support that, but I mean, it's perfectly feasible usage mode if you have light reinforcement, and if you basically are likely to get failing mechanisms reminiscent of those which you would see in a unreinforced masonry arch. How can I get the reactions for the pier and abutments? So, for example, if I have a pier in this particular example, I'll add a pier. So here we've got my analysis. If I zoom in and click on the contact, then I can get the normal force. The normal force is expressed as kilonewton per meter width. And I can also get the at right angles to that, the shear force. So 319 for the normal and 117 for the orthogonal. reaction force. Okay, I think we're running out of time, and I think we've also answered the questions. So I'll hand you back now to Tom just to wrap up the webinar.
Thank you, Matthew, and thanks everyone for attending. We've now reached the final part of the webinar. We hope that you learned something new about the software that maybe you didn't already know, and if the webinar's prompted any questions, then please get in touch via telephone or info@limitstate.com and we'll be happy to help you. For those of you who aren't current users of LimitState Ring, we'll be in touch over the next few days just to find out if you have any further questions and to see whether you think LimitState Ring might be a useful piece of software for you. If you would like to watch the webinar again, or if you think you might know somebody who would be interested to do so, then there'll be a recording available soon and we'll email you with a link once it's available online. We also have a collection of our previous webinars available to view on our YouTube channel, which you can visit at youtube.com/limitstatesoftware and see what's available. Also, if you'd like to look out for any event notifications that will be sent out via email and posted on our website, it will be at www.limitstate.com/events. Finally, I'd like to say thank you to everybody for listening and hope you can join us again in the near future. Thank you.